Hello, and thank you for joining me on this serene journey through time. Tonight, we will slowly drift into a state of calmness as we explore the ancient world of the rise and fall of dinosaurs, tracing the quiet story of their long reign across a changing planet. Imagine stepping softly onto vast prehistoric landscapes, where ferns and cycads sway gently in a warm breeze, and the distant calls of gentle dinosaurs echo across valleys carved by drifting continents. Feel the slow passage of deep time beneath your feet, the rise of forests, the shimmer of ancient lakes, and the subtle shift of mountains over millions of years. Picture early reptilian ancestors cautiously exploring sun-dappled clearings, the first true dinosaurs venturing into Triassic ecosystems, and later colossal creatures roaming the Jurassic plains under a golden sun. Notice the quiet moments of survival in unstable climates, the delicate balance between predator and prey, and the subtle signs of change as flowering plants begin to color the Cretaceous landscapes. With each breath, let yourself sink into this ancient rhythm, letting your mind drift gently through millions of years, observing the calm cycles of life, adaptation, and the eventual silence that followed their reign. If you enjoy these tranquil moments, please consider leaving a like, subscribing, or sharing your thoughts below. Your support is deeply appreciated and helps others discover this peaceful passage to the past. You can also turn on notifications so you don't miss any of our future journeys together. But for now, just breathe. Feel the earth beneath you, let your body relax, release any tension, and allow your mind to drift back to a world long ago. Let's begin. Long before the first dinosaurs walked across fertile plains, the Earth bore the deep, lingering wounds of catastrophe. The late Permian, over 250 million years ago, was a world still echoing with the aftershocks of the planet's greatest known extinction. In a relatively brief moment of geological time, more than 90% of species vanished. Oceans emptied of their vibrant diversity, leaving vast expanses of water still and somber. On land, the forests that once thrived in the humid, warm climates had succumbed to fire, drought, and the relentless march of atmospheric upheavals. Even the sky seemed altered, heavy with ash and clouds, casting a dim light upon landscapes stripped bare. Yet within this silence, life endured. Small, resilient amphibians persisted in the shadowed swamps. Early reptiles crept cautiously across volcanic plains, and hardy plants took root where nothing had dared before. Beneath the surface, the earth recorded its history in stone. Layers of sediment compacted over millennia preserved the footprints of creatures that had survived the extinction. They were faint impressions, easily overlooked, yet they spoke of life returning, of evolution's patient hand nudging the fragile survivors forward. These marks were whispers of endurance, of adaptation in the face of relentless change. The Permian scars were profound, yet they were not permanent. Life, though diminished, began the slow work of recolonization, inching back into rivers, marshes, and the skeletal remains of forests. In the flooded lowlands, small amphibians slithered through waterlogged soil, their movements deliberate and measured. They fed on insects and tiny crustaceans, creatures that had also endured the upheavals. Their presence was subtle, almost hidden beneath the delicate mats of algae and ferns that began to reclaim the banks of ancient rivers. These plants, stripped of competition, spread in cautious abundance. Their roots stabilized the mud, while leaves and stems trapped moisture, fostering microhabitats that nurtured the slow return of life. Every green tendril that broke through barren soil represented resilience. Every splash of movement in shallow water signaled an ecosystem in recovery. Further inland, volcanic plains told a story of fire and ash. Streams of molten rock had once scarred the terrain, sterilizing soil and reshaping the contours of the land. Yet over time, minerals leached into the cooling rock, creating pockets where early lichens and mosses could anchor. Reptiles, small and agile, began to venture across these plains, hunting the insects that had survived the fiery apocalypse. Their movements were cautious, deliberate, their bodies shaped by survival in a world still unforgiving. The skies above, darkened by lingering dust and the faint aroma of sulfur, lent the plains a muted, almost sepulchral atmosphere. Here, the first hints of evolutionary experimentation were visible. Limbs that could carry weight, claws that could grasp, and eyes that watched for both opportunity and threat. Shifting coastlines painted a different tableau. Rising and falling seas exposed mudflats and tidal channels, creating a mosaic of habitats. Fossilized footprints in these sediments revealed creatures moving in patterns both solitary and coordinated. Occasionally, small predators ventured near these waterways, leaving impressions of hunting strategies frozen in stone. The calm lapping of waves against desolate shores belied the underlying tension. Life had returned, but the balance was delicate. Predators and prey alike were attuned to scarcity, each movement a negotiation with the demands of survival. Atmospheric upheavals continued to shape these emergent ecosystems. Volcanic eruptions punctuated the horizon, releasing plumes of gas that altered weather patterns, while changes in carbon dioxide levels drove episodes of warming and cooling. The climate was volatile, yet in its instability lay the seeds of adaptation. Plants evolved subtle strategies to withstand heat and drought, while reptiles and amphibians refined behaviors that conserved energy and optimized foraging. The scars of mass extinction had imposed constraints, but these limitations were simultaneously laboratories for experimentation, teaching life how to persist under conditions both harsh and unpredictable. The Permian recovery was neither rapid nor uniform. Some regions remained barren for millennia, while others experienced pockets of thriving biodiversity. Early forests emerged slowly, with conifers and ferns forming the backbone of terrestrial ecosystems. Under the canopy, smaller plants, mosses, and lichens filled niches that might otherwise have remained empty. The soil, enriched by volcanic ash and decaying organic matter, slowly regained fertility. In these restored patches, insects flourished, their populations providing crucial sustenance for small reptiles and amphibians. Life crept back into existence, not with the grand spectacle of pre-extinction abundance, but with patient, meticulous persistence. Fossil evidence from this era allows us glimpses into these worlds. Skeletal fragments, tiny teeth, and impressions of skin or scales reveal a diversity often overshadowed by the scale of extinction. Footprints, preserved in stone for hundreds of millions of years, offer a unique lens into behavior, how creatures moved, hunted, and explored the reshaped terrain. Each layer of rock functions as a page in the Earth's chronicle, capturing episodes of survival, failure, and resilience. Every fossil is a whisper from a world almost lost, hinting at the slow emergence of the Archosaur ancestors who would one day dominate the Earth. The quiet resilience of life is evident in subtle interactions. Amphibians shared ephemeral pools with crustaceans and early insects, while small reptiles navigated rocky slopes in search of shelter or prey. Plant roots intertwined with soil, trapping water and stabilizing microenvironments for tiny colonies of life. Even in regions of relative barrenness, life left traces. A burrow, a chewed leaf, or a scattering of eggs carefully hidden in damp soil. These marks reveal both fragility and persistence, the duality that defines survival in a post-catastrophe world. In imagining these landscapes, one might drift through mist-laden swamps, where the first tentative croaks of amphibians fill the air, or across volcanic plains that glimmer with the faint sheen of hardened lava under a dim sun. Rivers meander slowly through desolate valleys, carrying sediment that will one day preserve the evidence of creatures moving along their banks. The wind whispers through newly sprouting ferns, rustling leaves in a rhythm almost musical in its consistency, a slow heartbeat of recovery that spans millennia. Even in stillness, the land seems to breathe, each inhalation a subtle promise that life continues, even against overwhelming odds. By studying these ancient terrains, we gain insight into the profound patience of evolution. It is not always marked by grandeur or speed, but by subtle persistence, incremental change, and the resilience of small forms. From the ashes of the Permian, life began to experiment anew, varying limb lengths, experimenting with new feeding strategies, and colonizing previously inhospitable niches. This careful, methodical progress laid the groundwork for future evolutionary marvels, including the earliest Archosaurs, the distant ancestors of dinosaurs, crocodiles, and eventually birds. Each fossil, each sediment layer, each trace of movement preserved in stone is a testament to the capacity of life to endure. The Earth before dinosaurs was a world of patient recovery, a testament to the quiet but unstoppable force of adaptation. From silent swamps to volcanic plains, from shifting coastlines to emergent forests, life persisted, layer by layer, footprint by footprint, organism by organism. And in that slow, deliberate resurgence, the stage was set for the creatures that would one day dominate the planet. A reminder that even in the wake of unimaginable loss, life finds a way to endure. In the lingering shadows of a world recovering from mass extinction, a remarkable group of reptiles began to take form, small, agile, and quietly formidable. These were the Archosaurs, ancestors of the dinosaurs, pterosaurs, and crocodilians that would eventually command Earth's landscapes. In the Triassic, approximately 245 to 230 million years ago, they were neither the colossal rulers of later ages nor the ostentatious predators of legend. Yet in their subtlety lay the foundations of evolutionary success, a careful orchestration of anatomy, behavior, and adaptability that would echo for millions of years. The Triassic continents were joined as Pangaea, a vast, sprawling landmass stretching from pole to pole. Its interior deserts, river valleys, and seasonal floodplains created a patchwork of habitats, each presenting distinct challenges and opportunities. In these diverse environments, early Archosaurs ventured cautiously, their upright limbs offering efficient locomotion across uneven terrain, their light, hollow bones enabling agility, and their respiratory systems promising endurance during long hunts or desperate flights from predators. They were small creatures, often no larger than a modern fox or large dog, yet their adaptations allowed them to explore niches that had remained vacant since the Permian. Along meandering rivers, where the water shimmered under a muted Triassic sun. Tiny Archosaurs darted between ferns and cycads, hunting insects and small amphibians. Their movements were deliberate, a balance of stealth and sudden bursts of speed, learned through countless encounters with predators and competitors. Fossilized trackways revealed traces of these journeys, etched into sediment that would harden over millennia. Parallel impressions suggest moments of social interaction, perhaps a pair moving cautiously together or a group navigating a flooded plain. Such patterns hint at the earliest stirrings of coordinated behavior, a quiet prelude to the complex social dynamics of their descendants. The Triassic climate was unpredictable. Arid, deserts could transform into seasonal torrents, sweeping away topsoil and redistributing life across floodplains. Vegetation responded in kind. Cycads, ferns, and seed ferns colonized exposed ground with tenacious persistence, creating corridors of food and shelter. Archosaurs exploited these transient opportunities, their keen senses detecting insect swarms, amphibian gatherings, or the faint rustle of a rival competitor. In these oscillating conditions, survival required both physical adaptability and behavioral acuity, a delicate interplay between instinct and environmental awareness. Small carnivorous archosaurs displayed remarkable diversity. Some hunted solo, relying on stealth and speed, while others may have exploited cooperative strategies, perhaps not unlike the pack behaviors observed in later theropods. Fossils of their skulls, jaws, and teeth indicate diets finely tuned to the available prey. Delicate incisors suggest insectivory, while slightly more robust jaws hint at the occasional amphibian or reptilian snack. In essence, each anatomical variation represented an experiment in survival, an incremental refinement of design in response to a world still healing from devastation. Across rocky highlands and sprawling plains, the Archosaurs encountered competitors, early synapsids, mammal-like reptiles that had persisted through the Permian, and other reptiles striving to reclaim the terrain. These interactions created subtle evolutionary pressures, shaping not only physical traits, but also behavioral patterns. Selection favored those capable of exploiting fleeting resources, avoiding predation, and reproducing successfully in unstable environments. Here, in the delicate dance of predator and prey, life was quietly refining itself, crafting the blueprint for the Mesozoic's eventual rulers. In the lowlands, ephemeral wetlands nurtured a different aspect of Archosaur life. Pools formed during seasonal rains, concentrating aquatic and semi-aquatic prey. Young Archosaurs, smaller and more vulnerable, found shelter among reeds and ferns, their limbs adapted for sudden bursts of swimming or clambering over mud. These microhabitats allowed survival despite competition from larger reptiles, illustrating the critical role of niche specialization in evolutionary success. Fossilized impressions of limbs and tail drags suggest that these early reptiles were adept swimmers, hunters, and climbers, a versatility that would echo through their descendants. The Triassic was not only a period of survival, but also of experimentation. Early Archosaurs exhibited traits that hinted at future dominance: upright posture for efficient locomotion, elongated limbs for pursuit and escape, and lightly built skeletons that maximized energy efficiency. Respiratory innovations, such as a flow-through lung system, allowed sustained activity even under the stresses of high heat or intermittent droughts. These adaptations were not sudden. They emerged gradually, shaped by the push and pull of climate, predation, and competition. Every minor adjustment increased the likelihood of survival, gradually sculpting lineages capable of withstanding both predictable and unforeseen environmental shifts. In examining the fossil record, we witness subtle migrations across Pangaea. As deserts dried and rivers shifted course, Archosaurs spread from isolated refuges into newly hospitable regions. Trackways suggest the occasional congregation at water sources or feeding grounds, while skeletal evidence reveals minor variations between populations. Incipient adaptations to local conditions, such as limb proportions or jaw structures. These variations were the whispers of evolution, quiet experiments that would, over millions of years, give rise to the first true dinosaurs. Vegetation played an equally vital role. Ferns, conifers, and ginkgo-like plants dominated landscapes, providing both nourishment and concealment. Insects thrived among these greens, forming a constant yet subtle supply of prey. The interplay between plant growth, insect populations, and small archosaurs exemplifies the intricate feedback loops shaping early ecosystems. Life was not abundant in spectacle, but it was rich in complexity, a web of interactions delicately tuned to the pressures of survival and the rhythm of environmental change. Triassic river valleys, dotted with volcanic outcrops, were theaters of persistence. Erosion exposed layers of sediment, where archosaur tracks, burrows, and occasional skeletal fragments would be preserved for hundreds of millions of years. Each footprint is a fleeting moment captured in stone. The careful placement of a claw, the cautious pause before a leap, the subtle dragging of a tail across soft mud. Such traces provide not only evidence of movement, but also insight into behavior, locomotion, and even social interaction. In these quiet imprints lies a profound story of adaptation, endurance, and the patient, iterative force of evolution. As the Triassic progressed, small archosaurs continued to diversify. Some began exploring new habitats, coastal plains, river deltas, and forested slopes. Each environment demanded adjustments, limbs capable of negotiating mud and sand, senses tuned to shifting shadows, diets flexible enough to exploit seasonal abundance or scarcity. These early experiments set a pattern of resilience, a template for the remarkable evolutionary success of their descendants. The stage was being quietly prepared for a world in which dinosaurs would eventually dominate, not through sudden conquest, but through millions of years of subtle, relentless refinement. The rise of Archosaurs is, in essence, a story of patient opportunity. The scars of the Permian extinction left empty niches, and in these voids, small, versatile reptiles began to flourish. Their successes were measured not in immediate grandeur, but in persistence. The survival of the fittest over countless generations, the quiet testing of anatomy and behavior, and the cautious exploration of a planet still healing. The Triassic world was harsh, unpredictable, and often unforgiving. Yet, within its flux, these early reptiles carved a path toward eventual dominance. By tracing their bones, footprints, and fossilized remnants, we gain a sense of the subtle pressures that guided evolution. Upright limbs, elongated torsos, and lightly built skeletons hint at a future where speed, agility, and endurance became central to survival. Respiratory systems designed for efficiency suggest sustained activity, while jaw and tooth adaptations reflect dietary flexibility. Each trait, each small innovation, was a step toward the complex, thriving ecosystems of the Mesozoic. In imagining this world, One drifts along dry riverbeds, where the sun glints off scattered stones and small archosaurs pause in the shade of ferns. The wind carries the scent of distant wetlands, and occasional plumes of volcanic ash darken the horizon. Insects buzz faintly, amphibians croak near hidden pools, and the first tentative calls of these reptiles echo softly. The land is alive with experimentation, resilience, and cautious expansion. A slow, deliberate unfolding of life that will, in time, culminate in the rise of the first true dinosaurs. By the late Triassic, roughly 230 million years ago, a new chapter in Earth's history was beginning. Among the recovering forests, river valleys, and arid plains, the first true dinosaurs emerged. Small, nimble predators and cautious herbivores, easily overlooked by larger reptiles that still dominated the landscape. These early creatures were neither massive nor imposing, yet their anatomy hinted at extraordinary evolutionary potential. Hollow bones reduced weight, elongated limbs, increased stride efficiency, and jaws and teeth adapted to a range of diets, setting the stage for a lineage that would shape terrestrial ecosystems for the next 165 million years. The Triassic world was unstable, a tapestry of deserts and floodplains, volcanoes and ephemeral lakes. Climate fluctuations were intense, swinging between periods of extreme aridity and sudden monsoonal rains that carved channels through a soft sediment. In these shifting environments, early dinosaurs exploited niches that had remained marginal, navigating terrain that challenged both predator and prey. Fossilized trackways reveal careful exploration. Small, bipedal predators moving in deliberate arcs. Herbivorous species weaving through ferns and low-growing plants, and both groups pausing at the edges of streams, their movement guided by instinct, terrain, and survival. These first dinosaurs were diminutive compared to the giants that would follow. Yet, in their form, evolution had begun an ambitious experiment. Limbs extended beneath their bodies, permitting greater speed and endurance than the sprawling gait of many contemporary reptiles. Their vertebrae were lightweight, yet strong, supporting active locomotion without sacrificing agility. Tail structures provided balance during sudden sprints or evasive maneuvers, while skulls, though modest in size, carried keen sensory adaptations for detecting prey or predator at a distance. In these subtle traits, one can see the blueprint of Mesozoic dominance gradually unfolding. Along the banks of river deltas, herbivorous dinosaurs grazed among dense mats of cycads and horsetails. Their teeth, serrated yet delicate, could process fibrous plant material, allowing them to exploit a variety of foliage. Juveniles clambered over roots and fallen branches, learning to navigate the complex undergrowth that sheltered them from predators. Meanwhile, small carnivores stalked the edges of these feeding grounds, eyes trained on movement, limbs poised to spring into action. Fossil evidence suggests that predation strategies included stealth, ambush, and sudden bursts of speed, revealing early experimentation with hunting techniques that would later be refined in large theropods. Volcanic highlands offered another arena for survival. Lava flows had cooled into jagged terrain, their dark surfaces absorbing sunlight and radiating heat. Here, dinosaurs adapted to thermally challenging environments. Herbivores foraged in shadowed gullies, while predators used the uneven landscape to conceal approach or retreat. The interplay between creature and environment became a dynamic lesson in endurance and adaptability. Every step, pause, or retreat reflected a careful negotiation with the world, a testament to the balance of risk and reward that shaped early dinosaur evolution. Diversity within these early dinosaur communities was already apparent. Small bipedal carnivores coexisted with lightly built herbivores, while the occasional omnivorous species bridged the gap between predator and prey. Fossilized stomach contents, when preserved, reveal a diet that spanned insects, small reptiles, and plant matter, highlighting behavioral versatility. This diversity allowed multiple species to occupy overlapping habitats without direct competition, illustrating the emergent complexity of Triassic ecosystems and the first experiments in niche partitioning that would define the Mesozoic. In floodplain forests, life was layered and intricate. Fallen trees provided shelter for fledgling herbivores, while underbrush concealed agile carnivores. Streams and ponds dotted the landscape, offering water and a concentration of prey. Fossilized footprints, often preserved in soft mud hardened by subsequent sedimentation, capture snapshots of movement, including the occasional pause to drink, scratch, or forage. These moments, frozen in time, reveal the rhythm of early dinosaur life, a slow yet persistent negotiation with the forces of predation, climate, and resource availability. Climatic volatility continued to shape evolutionary trajectories. Droughts forced herbivores to travel further in search of water, while predators adapted to tracking these movements over long distances. Heavy rains created temporary wetlands, which concentrated plant and animal life alike. The first true dinosaurs demonstrated remarkable flexibility in navigating these conditions. They were capable of rapid movement across uneven ground, sensitive to environmental cues, and able to exploit ephemeral resources, highlighting the adaptive foundation upon which later, more specialized species would be built. Evolutionary experimentation was not limited to size or diet. Sensory adaptations played a critical role in survival. Eyes capable of detecting subtle movement, olfactory senses tuned to prey or predator, and auditory perceptions sensitive to both distant calls and nearby rustlings allowed dinosaurs to navigate complex landscapes effectively. Fossil evidence of cranial anatomy suggests an emerging sophistication in brain structure, supporting coordination, balance, and hunting strategies. Over time, these traits would be refined, but in these early forms, the seeds of intelligence, agility, and social behavior were already evident. River valleys dotted with volcanic ash provide the richest snapshots of this period. Layers of sediment captured impressions of scales, claws, and footprints, recording the interplay of life and environment. In some cases, herds or groups of dinosaurs appear to have moved together, suggesting emergent social dynamics. Whether these were protective formations, hunting collaborations, or migratory gatherings remains speculative, yet the evidence points to behaviors increasingly responsive to both conspecifics and external pressures. Such subtle social structures offered a survival advantage, a lesson passed down through lineages that would eventually dominate terrestrial ecosystems. The Triassic landscape itself was a sculptor of evolution. Shifting coastlines, arid interiors, and volcanic activity created pockets of isolation and opportunity. Dinosaurs occupying marginal habitats faced challenges that selected for endurance, agility, and resourcefulness. These pressures gradually produced lineages capable of rapid diversification once the Mesozoic climate stabilized. Each riverbank, delta, and floodplain acted as both stage and crucible, where environmental uncertainty forged new adaptations and evolutionary trajectories. The first true dinosaurs, though modest in stature, exemplified a transformative moment in life's history. They moved with careful intent, hunted with strategic precision, and foraged with adaptability born of necessity. Their interactions with contemporaneous reptiles, amphibians, and early plants were the first steps in constructing the intricate web of the Mesozoic. Fossil evidence, when read carefully, conveys not spectacle but rhythm, a world alive with subtle motions, ongoing survival, and incremental innovation. In imagining these ancient landscapes, one envisions river deltas veiled in morning mist, ferns bending beneath gentle winds, and dinosaurs pausing at the water's edge, sensing movement or sound. Volcanic ridges in the distance emit faint plumes, while the sun casts long shadows across undulating terrain. Every impression in the mud, every broken branch, and every feeding mark tells a story of experimentation, endurance, and gradual adaptation. Here, in the turbulence of the late Triassic, the first true dinosaurs were learning to thrive, establishing patterns of movement, diet, and behavior that would endure for tens of millions of years. Through these formative landscapes, we witness the emergence of life that is both persistent and inventive. Small predators and cautious herbivores alike shaped and responded to their environments, embodying the delicate interplay between opportunity and constraint. The early dinosaurs' modest beginnings foreshadowed a lineage that would eventually rise to dominate forests, plains, and coastal lowlands, a testament to the enduring influence of incremental change and adaptive innovation. The Triassic period was a world in flux, a time when the Earth's surface was still responding to the massive upheavals of the Permian extinction. Vast deserts stretched across the supercontinent of Pangaea, interrupted by narrow river valleys and seasonal floodplains. Monsoons swept across parched lands, carving deep channels and creating temporary wetlands. Volcanoes punctuated the horizon, their ash clouds influencing climate and soil composition. Within this mosaic of extremes, life persisted, fragile yet remarkably inventive, evolving strategies to endure in an environment that demanded constant vigilance. Lowland plains, thick with cycads, ferns, and horsetails, offered both food and shelter to the early dinosaurs and their contemporaries. These dense plant communities were punctuated by streams and ponds, forming dynamic microhabitats that could sustain small herbivores, insectivores, and semi-aquatic reptiles. Juvenile dinosaurs moved carefully through the undergrowth, avoiding predators while learning to navigate uneven terrain. Fossilized trackways reveal patterns of movement, small deliberate steps crossing soft mud, occasional pauses to forage or drink, and subtle signs of interactions within groups. Each footprint preserves a moment of survival, a record of life adjusting to a capricious environment. Arid regions presented starkly different challenges. Sparse vegetation forced herbivores to range widely, seeking pockets of greenery amid cracked soil and shifting dunes. Predators, from lightly built Archosaurs to emerging theropods, learned to exploit these patterns, following prey across long distances and waiting near ephemeral water sources. Survival here demanded endurance, keen perception, and adaptive behavior. Fossils of limb structure and musculature suggest that many Triassic dinosaurs had evolved for sustained movement across challenging landscapes, their bodies refined for agility and efficiency. Rocky highlands and volcanic slopes created another distinct environment. Lava flows cooled into jagged ridges, their surfaces reflecting sunlight and intensifying heat. Plants grew in crevices and sheltered gullies, forming isolated pockets of sustenance. Here, armored reptiles and small herbivorous dinosaurs utilized the terrain for concealment, while carnivorous species developed strategies for ambushing prey along narrow pathways or cliff edges. These highlands served as laboratories for adaptation, forcing species to refine movement, sensory perception, and survival tactics. Fossil evidence indicates that early mammals and mammal-like reptiles shared these habitats, adding complexity to the ecosystems. Small nocturnal creatures took advantage of niches left by diurnal dinosaurs, foraging in shadows and using burrows for protection. Interactions between species were subtle yet consequential. Competition for resources, predator-prey dynamics, and accidental encounters shaped evolutionary pressures. Each organism, no matter how small, contributed to the intricate web of life, creating feedback loops that guided the development of traits that would become central to later Mesozoic fauna. The Triassic was also a time of experimentation in behavior. Some dinosaurs and archosaurs displayed early forms of sociality, evident from trackways suggesting group movement or herding behavior. Burrows, nests, and fossilized remains of juveniles indicate parental care and territoriality in certain species. Flight experiments may have begun in small, feathered archosaur relatives, testing gliding from low heights or leaping between branches in dense forests. These early behavioral adaptations were incremental, refined by generations of trial, survival, and environmental feedback. Waterways formed the lifeblood of the Triassic ecosystem. Rivers, streams, and temporary ponds provided hydration, food, and habitat diversity. Aquatic insects, amphibians, and fish thrived in these waters, attracting predators and offering herbivores access to lush plant growth along the banks. Seasonal flooding redistributed sediment, reshaped channels, and created new habitats, which in turn influenced migration patterns and feeding strategies. Fossilized impressions of aquatic plants and ripple marks in sediment illustrate the dynamic interplay between water and life, highlighting how environmental change could simultaneously challenge and enrich the landscape. The Triassic climate, while variable, influenced evolutionary trajectories profoundly. Prolonged droughts selected for species capable of endurance and resourcefulness, while wetter intervals favored those that could exploit temporary abundance. Plant growth, in turn, responded to these cycles, influencing herbivore distribution and shaping predator strategies. Fossilized pollen and spores reveal the proliferation of ferns, cycads, and early conifers, creating both food sources and cover for foraging animals. These patterns of growth and decline form the backdrop for a delicate balance, where survival depended on adaptability, timing, and responsiveness to shifting conditions. Predator-prey interactions defined much of the behavioral landscape. Small carnivorous dinosaurs hunted insects and amphibians, while larger theropods pursued herbivorous dinosaurs across plains and hills. Injuries preserved in fossilized bones, healed fractures, and trackways tell stories of encounters, escape, and endurance. Ambush, chase, and evasion were repeated endlessly across generations, gradually shaping anatomy, agility, and cognition. Subtle signs of cooperation, either in hunting or protection, hint at evolutionary experimentation in social behavior, long before complex pack structures emerged in later eras. Vegetation structure dictated more than just diet. shaped movement, reproduction, and even survival strategies. Dense forests provided refuge for juveniles, concealment for ambush predators, and corridors for migration. Open plains allowed herds to detect predators from a distance, yet demanded speed and stamina to traverse barren stretches. These environmental pressures reinforced adaptations in limb structure, sensory systems, and group behavior. Early dinosaurs were learning to interpret landscapes not merely as static backdrops, but as active participants in the drama of life and death. Triassic ecosystems were also theatres of evolutionary competition and innovation. Archosaurs and other reptiles explored new ecological roles, sometimes overlapping in habitat or diet. Fossil evidence suggests convergent evolution, unrelated species independently developing similar adaptations to cope with shared pressures. Body size, limb proportions, dentition, and sensory structures reflected these experiments, demonstrating the interplay of opportunity and constraint. Life was not abundant in spectacle, yet every interaction, whether chase, retreat, or feeding, pushed species along new evolutionary paths. Across floodplains and rocky ridges, every aspect of life was influenced by the rhythms of the environment. Diurnal and nocturnal cycles dictated activity. Rainfall and drought shaped movement and availability of food. Volcanic activity and sediment deposition redefined habitats. Fossils capture these rhythms through trackways, preserved burrows, and sedimentary layers, offering glimpses into how species adapted over time. In these patterns, we see the Triassic world as a complex, interconnected system where survival required ingenuity, flexibility, and timing. By the end of the Triassic, these ecosystems had produced lineages capable of withstanding instability and exploiting emerging niches. Small herbivores, agile carnivores, armored reptiles, and early mammals had all contributed to a balanced yet dynamic environment. The lessons of endurance, adaptability, and experimentation established during this period laid the groundwork for the explosive diversification of the Jurassic, when dinosaurs would rise to dominate forests, plains, and river valleys. Imagining these landscapes, one can see riverbanks lined with ferns, herds of small herbivores grazing amid cycads, and agile predators moving with careful calculation. Monsoon rains transform arid valleys into temporary wetlands, while volcanic ridges cast long shadows over plains dotted with trackways. Even in apparent stillness, life pulses with activity, movement, feeding, evasion, and adaptation. Each element, from insect to dinosaur, contributes to the evolving narrative of survival, demonstrating resilience, innovation, and the subtle interplay of species within a shifting, demanding world. The Triassic ecosystem, in its complexity and instability, is a reminder that evolutionary progress often unfolds in incremental, almost imperceptible steps. Adaptations emerge, behaviors are refined, and species navigate landscapes shaped by both geological and climatic forces. In this slow, unfolding drama, early dinosaurs and their contemporaries honed the traits that would allow them to thrive in the Mesozoic, ensuring that the story of life continued to expand, diversify, and endure. As the Triassic drew to a close, Earth's climate began to stabilize. Rivers ran more predictably, and lush vegetation spread across expanding floodplains and forested lowlands. The Jurassic period emerged as a time of grandeur and abundance, a world where life flourished on an unprecedented scale. Dinosaurs, once modest in size, began to expand both in form and ecological influence. Towering sauropods grazed among conifer forests, their immense necks reaching foliage that smaller herbivores could not access. Theropods, increasingly formidable, prowled the plains and woodlands with patient precision, hunting with intelligence and persistence honed over millions of years of evolutionary experimentation. Vast landscapes unfolded beneath expansive skies. Rolling plains, dense forests, and braided rivers provided a rich and varied stage for life to grow in both size and diversity. Sauropods moved in slow, purposeful herds, their massive limbs pressing into soft mud, leaving deep impressions that would become fossilized across eons. Their sheer scale influenced the surrounding vegetation. Branches snapped under their weight, undergrowth compressed beneath their movement, and rivers shifted as they sought foraging grounds. These giants reshaped their environment as much as they were shaped by it, a dynamic interplay of organism and habitat that would define the Jurassic. Herbivorous dinosaurs were not alone in this landscape. Armored species, such as stegosaurs, patrolled the margins of forests, their plated backs offering defense against increasingly large predators. Smaller ornithischians foraged in the undergrowth, exploiting niches created by the towering herbivores above them. Fossilized remains suggest these animals were often solitary, but occasionally congregated near water sources, forming temporary assemblages dictated by environmental opportunity rather than permanent social structures. Each species, in its own way, navigated the balance between abundance and risk, feeding and protection. Predatory dinosaurs, meanwhile, evolved in parallel with their prey. Theropods developed powerful hind limbs, elongated claws, and serrated teeth capable of cutting through flesh. Fossilized skeletons indicate muscular builds designed for bursts of speed, while tracks reveal careful stalking behavior across forested terrain and open plains alike. Some species hunted alone, relying on stealth and strength, while others may have employed coordinated strategies to ambush herds. Evidence of injuries on prey animals and healed fractures suggests repeated encounters, showing the slow, methodical rhythm of predator-prey interactions over extended periods. The expansion of life was accompanied by increasingly complex food webs. Aquatic and semi-aquatic ecosystems teemed with fish, amphibians, and small reptiles, supporting both terrestrial predators and opportunistic omnivores. Insects and other invertebrates proliferated, providing essential links in the chain of energy flow. Early mammals, still small and largely nocturnal, carved out niches in burrows, feeding on insects or plant matter, demonstrating that survival in a world dominated by dinosaurs required ingenuity, flexibility, and timing. The Jurassic landscape, in its richness, offered a delicate balance where multiple species coexisted, each shaped by the availability of food, shelter, and the presence of others. The evolution of gigantism was a hallmark of this era. Sauropods achieved extraordinary lengths, their vertebrae and limb structures engineered to support massive weight while maintaining mobility. Fossil evidence, including trackways and coprolites, provides insight into diet, migration patterns, and herd dynamics. These enormous creatures were not solitary anomalies, but integral parts of ecosystems, influencing vegetation growth, dispersing seeds, and creating pathways through forests. Their presence dictated the behavior of predators and smaller herbivores alike, shaping patterns of movement and survival across vast territories. Forests, meanwhile, became theaters of subtle interactions. Early birds, small feathered dinosaurs, and arboreal reptiles explored the canopies, hunting insects or seeking refuge. The structure of trees, tall conifers, cycads, and ferns, created a multi-layered environment where life could specialize in height, agility, or camouflage. Fossilized impressions of leaves and insects, along with preserved skeletal remains, suggest that these niches were rapidly occupied, illustrating nature's capacity for innovation in the context of abundant resources. Water systems continued to shape landscapes and behaviors. Rivers carved valleys, created deltas, and sustained wetlands that became hotspots of biodiversity. Sauropods often congregated near these rivers, drinking, foraging, and moving in unison across floodplains. Predators adapted to these congregation points, learning to navigate both land and shallow waters to access prey. Seasonal flooding redistributed nutrients, facilitated plant growth, and created transient habitats that encouraged migration, experimentation, and survival strategies across species. Social behaviors were increasingly apparent. Evidence from fossilized trackways suggests herding, coordinated movement, and territorial awareness among herbivorous dinosaurs. Juveniles learned to navigate alongside adults, gaining protection and observing foraging techniques. Predators may have shown early coordination, responding to prey movements with timing and precision. These interactions indicate that behavioral complexity was developing in parallel with physical adaptation, enhancing survival within increasingly populated and competitive environments. Interactions extended beyond animals. Plants shaped habitats and food availability, influencing migration, diet, and predator-prey dynamics. The proliferation of conifers, ferns, and cycads provided both sustenance and shelter. Fallen trees created obstacles and hiding places, while root systems stabilized soil, affecting water flow and sediment deposition. Life and landscape were intertwined. The largest dinosaurs reshaped their environment, while plant communities responded in turn, creating an intricate, self-modifying ecosystem that would remain resilient over millions of years. Migration patterns emerged as a consequence of resource availability and environmental stability. Sauropod herds moved across vast distances, following seasonal plant growth, while carnivores tracked their prey or exploited river corridors. Fossil evidence from multiple sites indicates repeated routes, suggesting an understanding of landscape over time. These migrations, though slow by human perception, represented a profound ecological rhythm, a movement of life that shaped the composition, distribution, and evolution of species across continents. The Jurassic era was not merely a period of expansion, it was a time of refinement and interconnectedness. The size and diversity of life forms introduced new challenges, leading to selective pressures on endurance, agility, social interaction, and adaptability. Fossilized bones, trackways, and plant impressions provide snapshots of these interactions, revealing ecosystems that were vast, dynamic, and balanced. Predators and prey, herbivores and carnivores, trees and insects, all moved within a web of dependencies, each influencing the other in subtle but enduring ways. In imagining the Jurassic, one envisions plains stretching toward distant horizons, punctuated by forests and winding rivers. Towering sauropods traverse these lands with a slow, rhythmic weight. Armored dinosaurs patrol the forest edges. Carnivores stalk with patience and calculated effort. Birds and small feathered dinosaurs flit among branches. Insects hum through ferns, and early mammals scurry in the shadowed undergrowth. The interplay of size, movement, and behavior conveys the richness of a world balanced between abundance and vigilance, growth and adaptation. The Jurassic expansion, in all its scale and complexity, laid the foundation for the ecosystems that would dominate the Mesozoic. Here, the Earth's biosphere reached a crescendo. Life became larger, more interconnected, and more intricate. Every footprint, feeding mark, and fossilized bone tells a story of adaptation, endurance, and subtle orchestration across millions of years. It was a world of both spectacle and refinement, a slow unfolding of life's potential, where the age of giants began in earnest, shaping landscapes and establishing patterns that would echo through time. Amid the grandeur of the Jurassic giants, a subtler revolution was taking place. In the undergrowth of dense forests, among ferns, cycads, and conifers, smaller dinosaurs were exploring forms of life that would ultimately redefine the skies. Feathers, delicate and filament-like at first, appeared along limbs and tails, serving purposes that were far more than ornamental. They provided warmth, insulation against fluctuating temperatures, and camouflage among dappled sunlight and shadows. These early adaptations, subtle yet transformative, were the first steps toward the extraordinary capability of flight. Small theropods, nimble and alert, moved with a precision dictated by both instinct and anatomy. Fossil evidence shows elongated forelimbs, hollow bones, and feathers aligned along the arms and tail, features that hinted at an untapped potential for gliding or controlled leaps. In the shadow of towering sauropods and armored stegosaurs, these diminutive creatures explored arboreal niches, leaping between branches and clambering up tree trunks. Their lives were shaped by an intricate balance of predation risk, foraging opportunity, and environmental variability, a dynamic that favored the experimentation of movement and anatomy. Forests of the Jurassic, with their towering trees and layered vegetation, created a three-dimensional world in which flight could be gradually tested. Feathers enhanced balance and agility, allowing small dinosaurs to navigate complex branches, evade predators, and pursue insects or small vertebrates. Fossilized impressions from China and other sites reveal a remarkable diversity of feather types, from simple filaments to structures resembling modern wings. Each variation represents an evolutionary experiment, a trial in both survival and the manipulation of air currents. The anatomy of these early flyers was a careful orchestration of lightweight structure and functional design. Hollow bones reduced mass without sacrificing strength, while elongated forelimbs and tails provided stability and maneuverability. Muscle attachments and joint flexibility indicate that these animals could generate controlled movements, from gliding to flapping. These incremental advances, reinforced by survival pressures, demonstrate how evolutionary pathways can explore multiple solutions to environmental challenges, testing the limits of form and function. The presence of larger dinosaurs created an indirect opportunity for these smaller species. Predators focused on herbivores or other theropods, leaving niches of relative safety in the forest canopy or along the edges of floodplains. Here, feathered dinosaurs could forage, experiment with locomotion, and occupy habitats unavailable to ground-bound competitors. Survival favored creativity. Those capable of exploiting new spaces and resources thrived, while those less adaptable disappeared from the fossil record. Nature was a patient teacher, guiding the emergence of flight through countless iterations over millions of years. In addition to facilitating movement, feathers played a role in thermoregulation and signaling. Variation in feather density, length, and structure allowed these dinosaurs to maintain body temperature in environments that could shift rapidly from sunlit warmth to shaded coolness. Display patterns may have assisted in mating rituals or territorial behavior, hinting at social interactions that extended beyond simple survival. These functional innovations were subtle but profound, laying the groundwork for more sophisticated adaptations in later periods. The forests themselves acted as both challenge and opportunity. Dense undergrowth required agility and rapid reaction times, while taller trees offered protection from ground-based threats. Streams, ponds, and rivers provided water and food, but demanded navigational skill. Fossilized tracks of small feathered dinosaurs suggest careful, deliberate movement, interspersed with sudden leaps or bounding strides. These interactions illustrate the delicate balance of risk and reward, shaping morphology and behavior through environmental pressures that were both immediate and cumulative. Flight was not immediate. It evolved gradually through stages of experimentation. Gliding between branches allowed animals to cover more territory, escape danger, and access food sources otherwise unreachable. Some species may have engaged in short bursts of flapping, testing aerodynamic principles in controlled movements. These behaviors were reinforced by survival and reproductive success, creating feedback loops that refined limb structure, muscle strength, and feather arrangement. Fossils reveal a spectrum of capability, from primitive gliders to species approaching true powered flight, each a milestone in the evolutionary journey. While the giants of the Jurassic commanded attention, these smaller feathered dinosaurs were quietly innovating. They were shaping a legacy that would outlast the enormous sauropods and formidable theropods, connecting the Mesozoic to the modern avian world. Fossil evidence demonstrates the continuity of form and function, bridging millions of years between non-avian dinosaurs and early birds. The forests, with their layered complexity, provided both a laboratory and a refuge for these evolutionary experiments, highlighting the interplay of environmental opportunity and adaptive potential. Insects and small vertebrates played a key role in the lives of these emerging flyers. Predation strategies required precision and dexterity, reinforcing anatomical innovations in wing and tail feathers. The availability of food-shaped foraging behavior, flight techniques, and spatial awareness. Survival depended on the integration of sensory perception, physical capability, and environmental understanding. A triad that ultimately drove the refinement of wings capable of sustained movement through air. Feathered dinosaurs were also part of broader ecosystems in which they interacted with plants, larger reptiles, and early mammals. Understory vegetation provided protection, insects offered sustenance, and ephemeral water sources guided patterns of movement. These interactions highlight the complex dependencies within Jurassic ecosystems, demonstrating that innovation occurred not in isolation, but within the context of interwoven ecological relationships. Each adaptation, each behavioral trial, was shaped by the pressures and opportunities presented by coexisting species and the landscapes they occupied. The gradual evolution of flight represents a convergence of factors: anatomical adaptation, behavioral experimentation, environmental structure, and ecological opportunity. Fossils preserve these incremental changes, from filament-like feathers to aerodynamic wing structures, illustrating how small modifications accumulated over generations to produce profound functional shifts. Each stage of this transformation embodies the interplay between survival, experimentation, and the selective pressures of a rich and dynamic world. Imagining the Jurassic forests, one can picture small feathered dinosaurs leaping between branches, adjusting wing-like limbs with careful precision and pausing to scan for prey or predator alike. The air carries subtle currents, influencing their movements, while sunlight filters through dense foliage, illuminating iridescent or patterned feathers. On the ground, sauropods graze, armored stegosaurs roam, and theropods patrol, largely unaware of the aerial experiments unfolding above. In this setting, the early origins of flight emerge as both a response to environmental challenge and a testament to the creativity of evolution. The story of feathered dinosaurs is a reminder that even amid the spectacle of towering giants, transformative innovation can occur in the smallest forms. By experimenting with feathers, limb structure, and behavior, these creatures began a trajectory that would eventually connect the Mesozoic to modern birds. In the process, they shaped the dynamics of forest ecosystems, influenced predator-prey relationships, and introduced a new dimension of mobility into Jurassic life. The subtlety of these changes, amplified across millions of years, illustrates the enduring power of evolutionary experimentation. As the Jurassic gave way to the Cretaceous, Earth's landscapes began to transform in ways both subtle and profound. Forests that had been dominated by cycads, conifers, and ferns now saw the first emergence of flowering plants, or angiosperms. These delicate botanical innovations introduced a new array of textures, colors, and nutritional resources into ecosystems that had previously relied on more monotonous plant life. The appearance of flowers and fruiting structures created niches that allowed a variety of dinosaurs and smaller creatures to explore previously unavailable diets and foraging behaviors, reshaping ecological relationships across entire continents. In lowland plains, early angiosperms formed meadows that swayed beneath the wind, interspersed with the towering silhouettes of conifers. Herbivorous dinosaurs, from small ornithischians to mid-sized hadrosaurs, moved through these landscapes with methodical patience. Their teeth adapted to chew and shred a wider variety of plant matter, while digestive systems evolved to extract nutrition from previously indigestible seeds and leaves. Fossilized gut contents reveal a mixture of conifer needles, ferns, and the softer tissues of early flowering plants, illustrating a transitional diet that mirrored the gradual reorganization of terrestrial ecosystems. Meanwhile, predators observed these changes, adjusting hunting strategies to exploit new patterns of prey behavior. Insectivorous theropods, small carnivores, and larger apex predators navigated increasingly complex vegetation, where dense flowering shrubs and low-lying meadows offered both cover and challenge. The interplay between predator and prey became more intricate as plant innovations indirectly influenced visibility, movement, and encounter rates. Fossilized footprints reveal stalking routes through flowering fields, where subtle changes in ground cover dictated both predator ambush and herbivore evasion. Waterways continued to structure ecosystems. Rivers, marshes, and deltas, shaped by seasonal rainfall and rising sea levels, provided life-sustaining corridors. These aquatic systems nourished riparian vegetation, which in turn supported a diverse array of herbivores. Fish Amphibians and aquatic invertebrates flourished in these habitats, providing sustenance for both semi-aquatic dinosaurs and small opportunistic predators. The combination of terrestrial and aquatic environments created mosaics of resources, encouraging migration, territorial behavior, and ecological specialization. Continental drift, slowly but persistently reshaping Earth's surface, created isolation and novel evolutionary opportunities. Populations of dinosaurs became geographically separated, allowing species to diverge in size, form, and behavior. Fossils from different landmasses reveal striking differences, from unique skull shapes to specialized limb structures, demonstrating that separation and environmental pressures drove adaptive experimentation. Islands and emergent coastal plains became laboratories of evolution, with local climates, vegetation, and predators shaping distinctive assemblages of flora and fauna. In addition to the emergence of flowering plants, insects underwent parallel diversification, responding to new sources of nectar and pollen. Pollination systems developed slowly as insects exploited floral structures for feeding, inadvertently transporting pollen and facilitating plant reproduction. This coevolution created intricate interdependencies. The spread of flowering plants depended on insect vectors, while insects benefited from previously untapped energy sources. Dinosaurs, insects, and plants together wove a tapestry of interactions that increased the complexity of food webs and ecosystem dynamics. Forest and meadow habitats supported vertical stratification of life. Canopies offered refuge to arboreal reptiles and early birds, while understory vegetation sheltered small dinosaurs and mammals. Flowering shrubs and low-lying plants provided foraging opportunities, while taller trees maintained microclimates of shade and moisture. This layered structure amplified biodiversity, creating conditions for both large and small species to coexist. Fossil impressions of leaves, pollen, and insects preserved in sedimentary deposits allow a reconstruction of these complex habitats, illustrating the multiple levels at which life interacted. Seasonal and climatic shifts further influenced Cretaceous ecosystems. Floodplains experienced episodic inundation, creating temporary wetlands that enriched soil fertility and stimulated plant growth. Arid periods induced competition, shaping foraging behavior, movement patterns, and herd dynamics. Dinosaurs adapted to these fluctuating conditions with both physical and behavioral strategies. Migration to resource-rich areas, burrowing or seeking shelter during extreme conditions, and social grouping to reduce vulnerability. These adaptations highlight the dynamic equilibrium between environmental variability and biological resilience. The emergence of flowering plants had cascading effects on herbivore evolution. Specialized dentition allowed for efficient processing of softer plant tissue, while jaw musculature evolved to handle both fibrous and tender vegetation. Some species developed selective feeding behaviors, targeting specific plants or plant parts, while others maintained generalized diets. The diversification of angiosperms provided dietary flexibility that could buffer herbivores against local environmental fluctuations, enhancing survival and promoting ecological stability. Predators, in turn, experienced indirect consequences. Herbivore abundance, influenced by plant diversity, affected predator distribution and hunting strategies. Forested meadows provided both concealment and challenge, necessitating agility, keen senses, and timing for successful predation. Trackways and fossilized injuries suggest that predation pressure remained a constant driver of anatomical and behavioral adaptation, with both predator and prey responding to shifting vegetation and resource patterns in ways that subtly shaped evolutionary trajectories. Flowering plants also altered reproductive behaviors. The production of seeds and fruit encouraged interactions between herbivores and their environment, including seed dispersal and selective feeding. This process, repeated across generations, contributed to the spread of plants into new habitats, enabling the colonization of diverse terrains and creating feedback loops between flora and fauna. These patterns enhanced landscape heterogeneity, further increasing the ecological opportunities for dinosaurs and other species. Through the lens of fossils, we observe the layered complexity of Cretaceous life. Leaves with bite marks reveal dietary choices, pollen grains show interactions with insects, and sedimentary structures indicate habitat distribution and seasonal changes. Large herbivores left footprints that trace migration routes across meadows and forests, while smaller species occupied niches in both canopy and understory. Every preserved element offers insight into the unfolding of ecological networks, demonstrating how subtle innovations in plants can ripple across entire ecosystems, shaping behavior, evolution, and biodiversity. In imagining Cretaceous landscapes, one can see meadows of flowering plants stretching under blue skies, interspersed with conifers and ferns. Herbivorous dinosaurs graze methodically, probing vegetation with specialized dentition, while small feathered species dart among shrubs, hunting insects or seeking refuge. Predators move with patience through dappled shadows, relying on stealth and timing. Streams and rivers curve through the land, sustaining lush riparian vegetation, while coastal plains advance gradually as continents shift and sea levels rise. Life thrives in layers, interconnected and adaptive, responding to both the emergence of new plant forms and the persistent pressures of climate, competition, and predation. The rise of flowering plants in the early Cretaceous marks a turning point, a botanical revolution that reshaped ecosystems, redefined diets, and amplified ecological complexity. Dinosaurs, insects, early mammals, and birds engaged with this innovation, creating a dynamic web of interactions that would persist and evolve through the remainder of the Mesozoic. Fossil evidence preserves these relationships in remarkable detail, allowing us to glimpse a world that balanced novelty with continuity, abundance with challenge, and growth with adaptation. In the flourishing landscapes of the Cretaceous, life existed within a delicate equilibrium, a continuous interplay between hunter and hunted. Vast plains, dense forests, and meandering rivers became arenas of tension where survival depended on strategy, endurance, and adaptability. Massive theropods, with their powerful limbs and serrated teeth, patrolled territories in search of herbivorous giants, while smaller carnivores hunted in packs, exploiting cooperation to corner swift prey. Every movement, every choice, was dictated by the need to feed, to avoid being eaten, and to ensure the continuation of a lineage that had endured millions of years. Large herbivores, from towering sauropods to plated and horned dinosaurs, navigated their habitats with a careful combination of vigilance and social behavior. Sauropods moved in herds, the youngest in the center for protection, the adults forming moving walls that deterred predators. Fossilized trackways suggest that these herds maintained structured formations, shifting slowly across floodplains and forests in search of nourishment. Smaller herbivores relied on camouflage, burrows, and rapid movements to avoid detection, their survival a constant negotiation with the predators that stalked the land. Predators shaped not only the behavior of their prey, but also the evolution of anatomical and social traits. Fossil evidence shows healed bite marks on bones, suggesting repeated encounters and narrow escapes. Injuries that healed indicate the persistence of both predator and prey, revealing the enduring struggle between survival and risk. Observing these interactions, one can infer the selective pressures that drove speed, agility, sensory development, and coordinated hunting behaviors. In this way, the predator-prey dynamic acted as a subtle sculptor of evolutionary innovation. Smaller carnivores, hunting in coordinated groups, demonstrated a sophisticated awareness of their environment. Fossil trackways reveal patterns of stalking, encirclement, and sudden bursts of pursuit. Such strategies required communication, observation, and timing, and these behaviors likely influenced both prey movement and habitat use. The complexity of these interactions underscores the role of behavior in shaping survival outcomes, illustrating that evolutionary success was as much about intelligence and adaptability as it was about size or strength. Waterways and wetlands were zones of concentrated interaction. Herbivores gathered at rivers to drink and feed on riparian vegetation, while predators lay in wait along banks or shallow waters. Seasonal flooding redistributed nutrients and created temporary marshes, influencing movement patterns and congregation points. These aquatic corridors offered both opportunity and peril, structuring encounters between species and amplifying the rhythm of life and survival. Fossilized footprints in soft mud provide snapshots of these moments, preserving the movements and interactions of creatures long vanished. The Cretaceous ecosystem was not a static battleground, but a dynamic network of relationships. Predator pressure influenced diet and foraging behavior, while prey abundance dictated territorial, ranges, and social structures. Camouflage, speed, herd size, and defensive adaptations evolved in response to these pressures. Fossil evidence, from claw marks to tail spikes, reveals the physical tools animals developed to survive, while trackways and nesting sites suggest behavioral strategies that allowed coexistence despite constant threats. Even smaller species participated in the dance of survival. Insects, mammals, and early birds navigated the same landscapes as larger dinosaurs, exploiting niches that minimized exposure to predation. Burrows, nocturnal activity, and arboreal habitats allowed these animals to avoid conflict while still securing sustenance. In doing so, they contributed to ecosystem stability, ensuring that energy flowed through multiple trophic levels and that life continued despite the omnipresent presence of danger. Interactions between predators and prey also influenced reproductive strategies. Herbivores timed breeding to coincide with periods of abundant vegetation, increasing offspring survival, while predators adjusted hunting strategies to the availability of juvenile prey. Fossilized nests, eggs, and hatchling tracks show patterns of care, concealment, and resource allocation, demonstrating that survival extended beyond immediate feeding and into the long-term perpetuation of species. These strategies, repeated over generations, reinforce the selective pressures driving both behavioral and anatomical evolution. Environmental changes, subtle or pronounced, affected these balances. Shifts in climate, vegetation, or water distribution could alter predator-prey dynamics, forcing migration, adaptation, or localized extinction. Seasonal droughts or floods tested resilience, while volcanic activity or shifting landscapes prompted the reorganization of habitats. Fossil evidence reveals variations in species composition across sites and time, reflecting these pressures and the responsiveness of ecosystems to ongoing challenges. Survival depended on constant observation, adjustment, and opportunistic behavior. In imagining the Cretaceous, one envisions a land alive with tension and rhythm. Sauropod herds move deliberately across meadows, their immense size deterring many predators, yet still vulnerable to the sharp teeth of large theropods. Packs of smaller carnivores coordinate silently, eyes fixed on agile prey. Ornithischians dart between flowering shrubs and ferns, alert to every rustle of leaves or shift in shadow. Streams and rivers host interactions that ripple across the landscape, shaping both behavior and evolution. Life is measured not in moments of spectacle, but in the continuous, deliberate negotiation between survival and threat. The fossil record preserves countless traces of these interactions. Healed injuries, broken bones, and bite marks speak to repeated encounters. Trackways reveal coordinated movement and herd behavior. Coprolites indicate diet and hunting success, while nesting sites provide evidence of protective strategies for the next generation. Together, these clues reconstruct the intricate web of life, emphasizing the importance of ecological balance and the ongoing pressures that drove adaptation and innovation. Through these dynamics, evolution acted as both sculptor and storyteller. Each predator-prey encounter contributed to the shaping of species, guiding anatomy, behavior, and ecological relationships over millions of years. The persistent negotiation of survival fostered specialization, resilience, and diversity, resulting in ecosystems capable of supporting both the largest and smallest inhabitants of the Cretaceous world. In this interplay, the survival of one species was inseparable from the existence of another, forming a continuously adapting and evolving network of life. From towering carnivores to diminutive insectivores, every creature participated in this dance. Adaptations accumulated slowly but inexorably, producing creatures exquisitely tuned to their environment. Predation encouraged defensive structures, cooperative behaviors, and innovative strategies, while prey dynamics guided dietary evolution, social organization, and habitat selection. Fossils capture the outcomes of these pressures, preserving a world in motion, alive with subtle tensions and enduring rhythms. The predator-prey balance of the Cretaceous was more than conflict. It was a system of checks and opportunities. Every encounter, every movement through forest, plain, or riverbed shaped the future of species, guiding evolution in ways that continue to influence life even today. The interplay of danger and survival, abundance and scarcity, strength and strategy, defined a world in which life persisted, flourished, and adapted over millions of years, leaving traces that whisper across deep time. As the Cretaceous progressed, subtle changes began to ripple across Earth's ecosystems. The landscapes that had once been abundant with flowering plants, ferns, and towering conifers now faced fluctuations in climate, vegetation, and resource distribution. These shifts were gradual but persistent, a slow press that tested the resilience of even the most dominant species. Fossil evidence from coastal plains, river deltas, and inland forests tells a story of communities responding to altered food availability, shifting habitats, and the pressures of competition intensified by environmental change. Herbivorous dinosaurs, from massive sauropods to smaller ornithischians, experienced the effects of these subtle transformations. Nutritional stress influenced migration patterns, herd size, and feeding behavior. Floodplains that once offered abundant vegetation occasionally became parched or submerged, compelling herds to relocate in search of edible foliage. Tracks in sedimentary layers suggest movement across hundreds of kilometers, revealing adaptive strategies to cope with unpredictability. Smaller species, especially those reliant on specific plant types, faced heightened vulnerability, with survival increasingly tied to flexibility in diet and habitat selection. Predators, too, felt the consequences of these environmental pressures. Large theropods depended on consistent populations of herbivores, while smaller carnivores hunted opportunistically. Fossil evidence reveals shifts in prey selection, healed injuries reflecting repeated encounters, and adaptations in hunting strategies to navigate changing terrain. Predation, which had long shaped anatomical and behavioral traits, now interacted with broader ecological stresses, creating layered challenges for survival. The evidence of environmental stress is also visible in plant fossils. Reduced diversity in some regions, variations in leaf size and structure, and the distribution of pollen grains indicate localized droughts or flooding events. Flowering plants, while adaptive, could not always maintain dominance in the face of climatic oscillations. Conifers and ferns reasserted presence in some areas, suggesting a dynamic reshuffling of plant communities. These botanical shifts rippled upward through the food chain, influencing herbivore diet and distribution, and, in turn, predator behavior. Volcanic activity further altered the landscapes. Ash layers preserved in sedimentary rocks reveal episodic eruptions that blanketed regions, temporarily sterilizing vegetation and contaminating waterways. Atmospheric particles affected sunlight penetration, influencing photosynthesis and temperature. Such events were intermittent yet impactful, creating periods of ecological strain that shaped species survival and drove adaptation over subsequent generations. Fossils capture these moments in layers, telling of repeated disturbances and the persistent resilience of life attempting to endure. Coastal regions, subject to both rising and falling sea levels, became sites of concentrated ecological pressure. River deltas shifted, estuaries expanded or contracted, and sedimentation patterns changed habitats. Herbivorous dinosaurs adjusted grazing routes, while aquatic and semi-aquatic species adapted to altered water flows. These changes highlight the interconnectedness of terrestrial and aquatic ecosystems, showing that stress in one component of the environment could cascade across multiple species and habitats. Fossilized remains provide insights into species-specific responses to stress. Some herbivores display evidence of stunted growth, malnutrition, or bone pathologies, indicating periods of scarcity. Predators, in turn, exhibit adaptations to exploit weakened or stressed prey. The fossil record reveals fluctuations in population density and species composition, suggesting that ecosystems were increasingly selective, favoring species capable of rapid adjustment and flexible behavior. Evolutionary pressures intensified as environmental variability increased. Migration and dispersal emerged as key strategies. Dinosaurs and other vertebrates navigated vast distances to locate suitable feeding grounds or nesting sites. Fossil trackways combined with sedimentary analysis, trace these movements across landscapes altered by both climate and tectonics. The ability to move, adapt, and locate resources became a determinant of survival, reflecting a deep connection between organism behavior and environmental conditions. Smaller species, including feathered dinosaurs, early mammals, and insects, occupied niches that offered relative refuge from widespread environmental stress. These microhabitats, whether shaded forest understories, riverbanks, or burrows, became critical for persistence. Fossilized remains in these protected zones reveal continuity even as larger ecosystems fluctuated, demonstrating that ecological stress was unevenly distributed, creating pockets of survival that maintained genetic lineages and preserved potential for future recovery. Interactions between species intensified under stress. Competition for food, territory, and mates increased, shaping behavior and morphology. Fossilized evidence of healed wounds, overlapping trackways, and predator-prey encounters suggests that survival required both caution and opportunism. Adaptive strategies that had once been advantageous in stable environments became essential under changing conditions, reinforcing the evolutionary link between environmental pressure and survival mechanisms. Climatic variation, including shifting temperatures, precipitation patterns, and seasonal extremes, further amplified ecosystem instability. Evidence from isotopic analysis of fossilized bones and teeth indicates fluctuations in water availability and diet. These changes influenced growth rates, reproduction, and social behaviors, affecting species across multiple trophic levels. The late Cretaceous emerges as a period in which the familiar rhythms of predator and prey, herbivore and plant, were increasingly punctuated by unpredictability and constraint. In imagining these landscapes, one sees herds of herbivores moving cautiously across meadows altered by drought, flooding, or vegetation shifts. Predators adjust their stalking routes, calculating opportunity amid uncertainty. Smaller creatures occupy niches where stability persists, taking advantage of relative safety and abundant micro-resources. Rivers shift course slowly over centuries, marshes expand and contract, and volcanic deposits occasionally blanket regions, creating a patchwork of challenge and opportunity. Life continues, but always under the increasing influence of change and stress. The fossil record preserves these patterns in meticulous detail. Layers of sediment tell of shifting coastlines, river paths, and flood events. Teeth marks and healed bones reveal the interplay of competition and survival under pressure. Plant fossils document shifts in diversity and abundance. Each piece contributes to a nuanced understanding of ecosystems responding to environmental stress, providing insight into the resilience, vulnerability, and adaptability of Cretaceous life. Ultimately, the late Cretaceous demonstrates that even dominant species are not impervious to environmental change. Subtle shifts, climatic fluctuations, volcanic events, or vegetation changes exert cumulative effects, testing the limits of adaptation. The ecosystems of this period reveal the fragile balance of life, where persistence depends on flexibility, movement, and the capacity to exploit new opportunities as landscapes evolve. Stress was no longer episodic, but a defining condition shaping evolutionary trajectories and setting the stage for the dramatic events that would soon follow. Beneath the slow drift of continents, a silent architect was shaping life in ways that would resonate across millions of years. As tectonic plates shifted and collided, landscapes were continuously redrawn. Mountains rose where seas had once lain, coastlines advanced or retreated, and islands emerged from the depths. These geological processes, imperceptible in a human lifetime, became powerful forces driving evolutionary divergence among the dinosaurs. Populations that were once continuous found themselves divided by newly formed oceans, mountain ranges, or arid expanses, each fragment of land presenting unique challenges and opportunities for survival. Isolation became a crucible for adaptation. Separated from their former relatives, dinosaur lineages evolved independently, their forms shaped by the particular climates, vegetation, and predators of their new environments. Fossils from South America, Africa, and Asia reveal astonishing diversity in skull structure, limb morphology, and body size, evidence of nature's patient experimentation in response to local conditions. Islands and continental margins acted as laboratories, where smaller populations adapted to limited resources, leading to dwarfing or specialized diets, while expansive plains allowed some lineages to reach immense proportions. Volcanic activity, closely tied to tectonic movements, further influenced habitats. Ash layers preserved in sedimentary rock document episodic eruptions, which altered soils, redirected waterways, and temporarily disrupted ecosystems. Species capable of adjusting their foraging, migration, or reproductive behaviors were more likely to persist, while others declined. Over successive generations, these pressures reinforced divergence among populations, demonstrating the intimate link between Earth's physical transformations and the trajectory of biological evolution. Marine incursions created by the rise and fall of sea levels along shifting continental margins introduced additional ecological variation. Coastal plains alternated between lush wetlands and dry expanses, prompting dinosaurs and other terrestrial species to adapt to fluctuating conditions. These transitions fostered mobility and dispersal, with trackways revealing long-distance movements in search of stable resources. Fossilized footprints preserved in sedimentary beds capture these migrations, hinting at responses to both opportunity and constraint imposed by a reshaped world. The drift of continents also facilitated the appearance of unique climates. As land masses moved toward or away from the poles, temperature and rainfall patterns shifted, creating deserts, monsoon-like regions, or temperate zones. Vegetation transformed in parallel, influencing herbivore diets and, consequently, predator strategies. This interaction between tectonics and climate reinforced ecological divergence. Species were forced to adjust not only to new physical landscapes, but also to the subtle fluctuations in available food and water. In isolated regions, convergent evolution occasionally produced striking similarities among unrelated species. For example, island-dwelling dinosaurs often evolved compact bodies and specialized feeding adaptations that mirrored traits seen on distant landmasses. Yet these similarities were the product of comparable environmental pressures rather than shared ancestry, illustrating how geography and circumstance could mold life in parallel yet distinct ways. Fossil evidence, from skeletal morphology to preserved behaviors such as nesting, provides glimpses of these independent experiments in adaptation. Migration corridors, sometimes created by temporary land bridges or shallow seas, allowed for episodic exchanges between separated populations. These rare connections permitted gene flow, occasional hybridization, and the spread of advantageous traits. but such opportunities were fleeting, leaving the majority of lineages to evolve along isolated paths. Fossil assemblages often capture abrupt shifts in species composition, reflecting both separation and intermittent reconnection over geological time. Beyond dinosaurs, continental drift influenced a host of other organisms. Early mammals, birds, and reptiles were affected by changing landscapes, as were plant communities. Flowering plants dispersed along shifting coastlines, adapting to new soil types and climatic conditions. Insects and pollinators followed these botanical expansions, creating networks of interdependence that were sensitive to geographic isolation. The fossil record preserves these complex ecological interactions, revealing that tectonic movements were not merely physical events, but evolutionary catalysts that affected every level of the ecosystem. Mountains, rising slowly over millions of years, created barriers and microclimates. Slopes harbored distinct vegetation zones, influencing the distribution of herbivores and shaping the predation strategies of carnivores. Valleys collected water and sediment, forming fertile niches that supported diverse communities. Over time, these elevated regions became refuges for species adapted to cooler temperatures or less disturbed habitats, while lowlands continued to host large mobile populations. Fossils found at varying altitudes demonstrate the subtle ecological partitioning that accompanied continental uplift. Volcanism, mountain building, and sea level changes also produced episodic stress events. Some regions experienced localized extinctions, while others witnessed the rapid proliferation of new species capable of exploiting transformed environments. This dynamic created a patchwork of biodiversity across continents, where survival depended on both flexibility and the ability to exploit new ecological niches. Species that adapted to isolation and resource variability flourished, while less adaptable lineages gradually vanished. In imagining the late Cretaceous world, one can picture a continent in flux. Rivers change course over centuries, mountains rise imperceptibly, and coastlines recede as seas encroach. Dinosaur populations, separated by newly formed deserts or waterways, evolve along distinct trajectories. Some become giants, exploiting abundant plains, while others shrink or specialize, thriving in constrained island habitats. Predators adapt to the prey available in each isolated environment, developing hunting strategies suited to local conditions. Life continues in constant negotiation with a shifting stage, each species a response to the slow rhythm of Earth's tectonic heart. The fossil record captures these transformations in remarkable detail. Skeletal adaptations reveal differences in limb mechanics and body size. Trackways indicate migration and territory use, and plant fossils document the environmental context of each lineage. Across continents, evidence demonstrates that isolation, environmental pressure, and opportunity combine to drive the spectacular diversity of the Cretaceous. Tectonic movement, almost imperceptible in the moment, was a master sculptor of evolutionary form, determining not only what species survived, but how they lived, moved, and interacted within their ever-changing worlds. Continental drift was a slow, inexorable force shaping the course of life. By dividing populations, creating new habitats, and altering climates, it imposed both constraint and possibility. Dinosaurs and other organisms responded with adaptation, innovation, and resilience, producing an array of forms uniquely suited to their isolated realms. In this interplay between Earth and life, geology and biology became inseparable, each guiding the other in a patient, unfolding dialogue that would continue to define the planet's inhabitants until the final days of the Mesozoic. By the late Cretaceous, Earth's ecosystems had reached a peak of complexity and interconnection, a tapestry woven over millions of years of evolution, adaptation, and subtle environmental change. Vast floodplains, dense forests, marshes, and coastal plains became vibrant arenas where countless species interacted, each movement and behavior contributing to a dynamic and balanced system. Giant sauropods grazed on towering conifers and cycads, their immense bodies reshaping landscapes as they moved in slow, deliberate herds. The very rhythm of their feeding created clearings, enriched soils, and pathways that smaller creatures would exploit, illustrating the interdependence that defined mature ecosystems. Among the herbivores, armored ankylosaurs and horned ceratopsians defended territories with specialized weapons and protective structures, establishing a hierarchy of space and resource use. Their interactions left traces in fossilized footprints, nests, and even damaged vegetation, preserving the story of coexistence and competition. Smaller herbivorous species, including early ornithopods, navigated understories and open plains alike, balancing feeding strategies against predator presence. These layered interactions created an intricate network in which each species influenced the survival and behavior of others, a silent choreography of ecological interdependence. Predatory dinosaurs maintained their pivotal role within these ecosystems. Massive theropods roamed across plains, stalking prey with deliberate patience, while smaller carnivores exploited agility and intelligence to capture food, hunt cooperatively, or scavenge opportunistically. Fossil evidence, including healed injuries and overlapping trackways, documents repeated encounters and adaptive strategies. Predators shaped not only population sizes, but also behaviors, fostering vigilance, social cooperation, and resource management among herbivorous species. The balance between hunter and hunted was a critical force maintaining stability within the system. Beyond the giants, a rich diversity of small species thrived in niches that leveraged the complexity of these habitats. Feathered dinosaurs, early birds, mammals, reptiles, and insects navigated the understory of forests, marshes, and riversides, each exploiting specialized microhabitats. Burrows, arboreal nests, and aquatic refuges offered protection, food, and breeding sites, allowing these species to persist alongside the larger dinosaurs. Fossilized evidence of these interactions, nests, eggs, and even traces of foraging, reveals how intricate relationships were maintained across multiple layers of the ecosystem. Flowering plants, angiosperms, now flourished alongside ferns and conifers, reshaping food sources and creating novel ecological opportunities. Their abundance supported herbivores with diverse diets, from massive sauropods that stripped branches to smaller species that nibbled on leaves and flowers. In turn, these plants influenced predator behavior, concentrating prey around feeding sites and dictating movement patterns. Fossilized pollen, leaves, and digestive remnants provide a window into these interactions, capturing the subtle interplay between vegetation and vertebrate life. Rivers, lakes, and wetlands acted as lifelines within these landscapes. Waterways provided nourishment, attracted diverse species, and facilitated migration. Sedimentary deposits preserve layers of interactions. Herbivores drinking at the water's edge, predators lurking in ambush, and smaller creatures taking advantage of abundant aquatic resources. These hubs became epicenters of ecological activity, fostering biodiversity and supporting food webs that extended across trophic levels. The constant movement of water reshaped terrain, deposited nutrients, and created environments where survival and opportunity were intimately linked. Social behaviors, too, flourished within these mature ecosystems. Evidence from nesting colonies, trackways, and group movement patterns suggests that some species exhibited coordinated activities, whether for defense, reproduction, or migration. Herding, territoriality, and pack hunting all reflect behavioral adaptations that strengthened survival within complex environments. These strategies were layered, nuanced, and often species-specific, reflecting an advanced ecological sophistication rarely captured outside of fossil evidence. Interactions extended to reproductive strategies. Nesting sites and egg clutches, preserved in sediment, demonstrate attention to protection and environmental conditions. Some species exhibited parental care, while others relied on concealment or abundance to ensure the survival of offspring. Predation risk, food availability, and habitat stability influence these strategies, creating a constant interplay between reproductive investment and ecological conditions. Fossil evidence of bite marks on eggs and hatchling tracks suggests that even reproductive stages were enmeshed in the web of survival. Despite the presence of colossal dinosaurs, mature ecosystems displayed balance. Plant-animal interactions, predator-prey dynamics, and interspecies competition coexisted without leading to widespread collapse. The interconnectedness of species, from microscopic insects to massive herbivores, ensured energy flow and nutrient cycling remained stable. Fossilized coprolites, trackways, and feeding traces document this delicate balance, revealing a complex yet functional ecological network. Each species played a role, contributing to the overall stability and resilience of the ecosystem. Environmental pressures, while persistent, had been largely mitigated by adaptation. Stable climates, diversified plant communities, and established migratory and social patterns allowed species to thrive. Yet subtle fluctuations, such as seasonal rainfall changes, local droughts, or volcanic ash deposits, reminded inhabitants that ecosystems remained sensitive to perturbation. These minor stresses were woven into the broader rhythm of life, shaping survival strategies without dismantling the overall structure of biodiversity. The fossil record offers a mosaic of ecological snapshots. Teeth marks, healed injuries, and coprolites reveal predator-prey dynamics. Trackways capture movement and herd behavior. Nests and eggs provide insight into reproductive strategies. Plant fossils record vegetation shifts and food availability. Together, these clues reconstruct a system defined not by the dominance of a single species, but by the interdependence of countless forms of life, from towering sauropods to diminutive birds, insects, and mammals. In this mature Cretaceous world, one can imagine the visual and sensory landscape. Herds of long-necked giants traversing sunlit floodplains, horned dinosaurs displaying territorial behaviors along forest edges, and feathered creatures flitting through dense understories. Rivers carry the murmur of life, wetlands shimmer with movement, and forest canopies conceal small, industrious inhabitants. Every element, from vegetation to apex predator, contributes to a living mosaic that thrives through interconnection and adaptability. Ultimately, the late Cretaceous represents ecological flourishing at its peak. The combination of biodiversity, intricate behaviors, and environmental complexity created a world capable of sustaining both the largest and most specialized species. Fossil evidence illuminates these systems, preserving the traces of interactions, adaptations, and subtle balances that defined this era. It is a portrait of life in equilibrium, alive with movement, strategy, and interdependence, a testament to the intricate beauty and resilience of Earth's ancient ecosystems before their dramatic upheaval. 66 million years ago, an event of unimaginable force struck Earth, changing the course of life forever. A massive asteroid, tens of kilometers in diameter, collided with the planet with energy equivalent to billions of nuclear detonations. The impact site, near the present-day Yucatan Peninsula, became a crucible of fire, smoke, and devastation. The collisions sent shockwaves rippling through the crust, triggering earthquakes, tsunamis, and volcanic eruptions, while ejecting vast quantities of molten rock and dust into the atmosphere. The immediate vicinity was obliterated in an instant. Forests vaporized, water bodies boiled, and creatures of every size were consumed by the initial blast. The heat radiating from the impact ignited fires that spread across continents, leaving charred landscapes in their wake. Sedimentary layers from this period preserve a global layer of soot and iridium-rich dust, evidence of an event so immense that its effects reached every corner of the planet. These deposits act as time capsules, recording the instantaneous disruption of ecosystems and the extinction of countless species. The atmosphere, thickened with particulate matter, transformed Earth into a shadowed world. Sunlight was blocked for months, disrupting photosynthesis and causing temperatures to plummet. Plants withered without light, herbivores lost their food sources, and predators faced starvation as prey disappeared. The collapse of the primary producers cascaded through the food chain, unraveling the intricate networks that had sustained life during the flourishing Cretaceous ecosystems. Fossil evidence shows abrupt declines in species diversity and density, a testimony to the widespread and rapid ecological collapse. Oceans were not spared. Tsunamis generated by the impact surged across coastlines, eroding shorelines and destroying shallow marine habitats. Aquatic species faced sudden habitat loss, and the disruption of plankton populations, the base of the marine food web, led to cascading extinctions throughout the seas. Sedimentary layers rich in shocked minerals and microfossils document this tumultuous period, offering glimpses into the global reach of the catastrophe. Ash and debris filled the skies for months, creating an extended winter-like condition known as an impact winter. With diminished sunlight, temperatures dropped and seasonal cycles were disrupted. Plants and phytoplankton failed to grow, leading to further scarcity of food for herbivores and, in turn, for the carnivores that relied upon them. Fossils from this period, showing evidence of starvation or stunted growth, testify to the severe and prolonged stress experienced by life across both terrestrial and marine ecosystems. Some areas experienced firestorms, ignited by the intense heat radiating from ejecta re-entering the atmosphere. These infernos incinerated vegetation over vast regions, leaving blackened soil and skeletal remains of countless organisms. Layers of charred plant matter and carbon-rich sediments, preserved over millions of years, provide a record of the destructive force that swept across continents. Even the largest and most formidable dinosaurs could not escape the immediate consequences of these firestorms, illustrating the sheer scale and indiscriminate nature of the disaster. Shockwaves traveled around the globe, fracturing the crust and triggering seismic activity far from the impact site. Volcanoes, already active in some regions, erupted in response to the stress, compounding the environmental strain. Lava flows, ash deposits, and gas emissions added to the atmospheric burden, further reducing light and altering climate patterns. This combination of geological and extraterrestrial events created a perfect storm of ecological disruption. Life's decline was not instantaneous everywhere, but it was pervasive. Fossils document a sequence of abrupt disappearance, followed by smaller pockets of survival. Certain lineages of plants, insects, and small vertebrates persisted in isolated refuges, exploiting microhabitats where food and shelter remained sufficient. Birds, mammals, and some reptiles survived in niches that larger species could no longer inhabit, demonstrating how size, adaptability, and ecological flexibility influenced survival. The global impact of this event extended beyond the immediate physical devastation. Atmospheric dust led to a prolonged reduction in temperature and photosynthetic activity, creating months and potentially years of inhospitable conditions. Food chains collapsed, and complex interactions that had sustained mature ecosystems unraveled. Coastal areas, inland, forests, and floodplains alike were transformed, leaving fossil evidence of widespread mortality, disrupted vegetation, and altered sedimentation patterns. In imagining this period, one can picture skies choked with ash, sunlight filtered into a dim twilight, and once thriving plains and forests silenced by fire and desolation. Rivers carried debris, and shorelines bore the scars of tsunamis. The world became a place of survival against overwhelming odds, where even the most dominant species were vulnerable to forces beyond their control. Fossils and sediment layers allow us to trace the unfolding of these events with remarkable clarity, revealing both the magnitude of destruction and the selective persistence of life. This moment marked the end of an era. The flourishing ecosystems of the Cretaceous, with their towering sauropods, agile predators, and intricate interdependencies, were brought to a near-complete halt. Yet even in this catastrophe, the seeds of the future persisted. Isolated populations, small and adaptable, endured to continue the story of life on Earth. Fossil evidence preserves both the devastation and the continuity, a testament to the interplay of extinction and survival in the aftermath of the asteroid impact. In the aftermath of the asteroid impact, the grandeur of the Cretaceous world gave way to a prolonged unraveling. Landscapes once rich with life became subdued and barren. Forests once alive with towering conifers and vibrant angiosperms were reduced to charred remnants, scattered branches, and leafless trunks. River systems, which had carried nutrients and supported diverse communities, slowed and silted, their banks littered with the remains of creatures that could no longer find sustenance. The ecosystems that had flourished with intricate balance for millions of years now struggled under the weight of a changed world. Giant herbivorous dinosaurs, reliant on abundant vegetation, faced the harshest challenges. Sauropods, their enormous bodies demanding vast amounts of foliage, wandered over depleted plains, stripping the few surviving plants, only to find new areas equally barren. Ceratopsians and hadrosaurs, adapted to grazing and browsing, faced a sudden scarcity of food. Fossilized stomach contents from this period indicate stunted growth, signs of starvation, and a marked decline in reproductive success. As plant life faltered, these megaherbivores dwindled, their populations fragmented and unable to sustain the complex social structures that had characterized their existence. Predatory dinosaurs, in turn, suffered the consequences of their prey's decline. Large theropods, once dominant hunters, struggled to find sufficient sustenance. Fossil evidence from bones-bearing injuries and healed fractures shows that some predators survived temporarily, but their numbers were diminishing. The collapse of herbivore populations cascaded through the food web, leaving apex predators isolated, increasingly malnourished, and unable to reproduce successfully. Small carnivores, more flexible in diet and behavior, fared slightly better, though even they faced dwindling resources and competition for limited habitats. Waterways, so central to ecosystem stability, carried their own record of change. Floodplains became sediment-choked, wetlands shrank, and lakes lost the aquatic vegetation that had supported fish, amphibians, and smaller reptiles. Sedimentary layers reveal a mixture of fossilized remains, from skeletal fragments to impressions of decayed vegetation, highlighting the gradual yet inexorable decline of life. Microhabitats that had once served as refuges persisted in pockets. Isolated marshes, coastal lagoons, and sheltered forests, allowing some smaller species to endure. Yet even these oases were fragile, constantly challenged by climatic shifts and the altered landscape. Amid this decline, survival was a matter of adaptability. Small size, dietary flexibility, and the ability to exploit marginal habitats determined which species persisted. Mammals, birds, and some reptiles exploited niches that were inhospitable to the giants. Fossil evidence shows continuity among these survivors, hinting at the traits that allowed them to navigate the changed world: flight, burrowing, scavenging, and omnivorous feeding habits. These survivors became the bearers of life's continuity, preserving lineages that would one day flourish in the absence of their giant predecessors. The landscape itself became a testimony to loss. Ash layers, volcanic deposits, and sedimentary shifts bore the marks of environmental stress. Forests gave way to scrubland and fern-dominated patches, and rivers meandered through sparse plains where vast herds had once grazed. Trace fossils, including isolated footprints and abandoned nests, indicate the diminished activity of species that had once dominated their territories. Each layer of sediment recorded both the absence and the faint persistence of life, a narrative of decline written into stone. Interactions between species that had defined the Cretaceous era changed fundamentally. Predation, competition, and social behaviors diminished in intensity as populations thinned. Herds broke apart, territorial boundaries became meaningless, and many complex behaviors were abandoned in the struggle simply to survive. Evidence from trackways shows fewer coordinated movements, and nesting sites become scarcer, suggesting the disruption of reproductive strategies. Ecological networks, once intricate and balanced, now resembled fractured threads of their former complexity. Even plants, the base of terrestrial food webs, faced profound stress. Angiosperms, conifers, and ferns survived in limited patches, but diversity declined. Pollen and leaf fossils from this period show reduced variety, a sign of both localized extinctions and restricted recolonization. The reduction of plant communities further reinforced the challenges for herbivores, amplifying the collapse across trophic levels. Ecosystems had lost the resilience that had supported towering herds and diverse communities for millions of years. Yet in the midst of decline, life clung to existence in pockets. Small refuges, shaded groves, river margins, and coastal lagoons harbored survivors. Mammals remained nocturnal, burrowing into protective shelters. Early birds and feathered dinosaurs exploited insect-rich microhabitats. Some reptiles persisted in water or concealed forested areas. Fossils from these survivors, although sparse, illustrate persistence against overwhelming odds, a testament to the selective forces that favored adaptability over size or dominance. The collapse was gradual, measured in decades and centuries on geological timescales. It was not the sudden obliteration of life that the asteroid impact initially caused, but a drawn-out decline, a slow fading of ecosystems that had once been lush and intricate. In these final moments for the giants, traces of their former presence remained. The last tracks in sediment, broken branches from feeding, and skeletal remains left where death overtook life. Each of these relics speaks to the passage of an era, the end of dominance, and the transition to a world increasingly shaped by smaller, adaptable species. In envisioning this period, one can picture plains once filled with immense herds, now sparsely inhabited by scattered survivors. Forests, once dense and teeming, are patchy and fragmented. Rivers, previously busy with life, flow through empty corridors. The echoes of the giants linger in bones and footprints, but the rhythm of life has shifted. What had been a world defined by size and strength is transformed into a realm of endurance, flexibility, and survival in the margins. Fossils preserve both loss and legacy. Each fragment tells a story of struggle, adaptation, and the narrowing of possibility. Yet within this narrative of decline, there are seeds of continuity. While the age of giants ended, the survivors, small, versatile, and adaptable, set the stage for the reorganization of life that would follow. Their persistence foreshadows the rise of new ecosystems, shaped not by colossal forms, but by species able to navigate a radically altered planet. In the shadow of catastrophe, life clung to fragments of opportunity. Among the devastation left by the asteroid impact and the ensuing collapse of ecosystems, a select few lineages endured. Notably, the ancestors of modern birds persisted, small and adaptable, navigating landscapes that had become inhospitable to giants. The survival of these creatures was not a matter of chance alone. It was a testament to evolutionary traits, finely tuned for resilience in a changing world. These early birds and their close relatives were modest in size, often weighing little more than a modern pigeon, yet this smallness proved advantageous. Where colossal herbivores and predators required vast amounts of food, these diminutive species could subsist on limited resources: seeds, insects, and small invertebrates. Fossilized stomach contents reveal diverse diets, indicating opportunistic feeding strategies that allowed survival in patchy habitats. The ability to exploit multiple food sources, combined with flexibility in habitat selection, created a buffer against the extremes of post-impact scarcity. Flight, whether in short bursts, gliding, or more sustained patterns, offered another critical advantage. Aerial mobility allowed these survivors to escape ground-level hazards, reach isolated refuges, and locate food sources inaccessible to larger grounded species. Fossil evidence from wing bones, feather impressions, and skeletal adaptations demonstrates the gradual refinement of flight mechanics, from simple gliding structures to more robust aerodynamic forms. This capability extended not only the range of these creatures, but also their potential for colonization across fragmented habitats, from surviving forests to coastal enclaves. Feathers, already present in these species for insulation or display, also provided camouflage, helping them avoid predators in a landscape now dominated by environmental unpredictability. Patterns preserved in fossilized feathers suggest an interplay of coloration and texture that aided concealment in dappled light beneath recovering foliage. Feathers, multifunctional in nature, were instrumental for warmth, survival, and eventual aerodynamic experimentation that would lead to the diversity of flight observed in birds today. Small size, coupled with flexibility and mobility, allowed these survivors to exploit microhabitats often overlooked by larger organisms. Shaded forest understories, coastal mangroves, and river margins offered shelter and resources. Burrows, hollowed trees, and debris provided protection from both environmental extremes and residual predatory threats. Fossilized remains indicate that these refuges were crucial for nesting and reproduction, enabling populations to endure when other habitats were compromised or destroyed. Adaptability extended beyond diet and shelter. Behavioral plasticity allowed these early birds to adjust to changing conditions. Some species may have been opportunistic scavengers, while others relied on insectivory or seed gathering. Fossils from the aftermath of the mass extinction show subtle shifts in body proportions and limb structures, evidence of selection favoring efficiency in movement, feeding, and energy use. In this new world, the capacity to modify behavior according to available resources and environmental pressures determined survival more than size or predatory dominance ever could. Reproduction itself required adaptation. Nesting strategies, evidenced in fossilized clutches, indicate that these species sought sheltered, protected locations for laying eggs, reducing the risk of predation and environmental damage. Smaller clutch sizes and the selection of hidden sites may have been a response to limited food availability, balancing reproductive investment against survival risk. The continuity of these reproductive adaptations ensured the persistence of lineages in a landscape where survival depended on subtle efficiencies and strategic behaviors. Fossils provide a bridge across this turbulent transition. Skeletal features reveal a lineage linking non-avian dinosaurs to early birds, capturing the continuity of traits and adaptations. From clawed feet to elongated forelimbs and the evolution of specialized respiratory systems, each anatomical detail tells a story of survival under pressure. The persistence of these lineages underscores the selective advantage of traits that were, in essence, pre-adaptations for navigating post-catastrophe ecosystems. While the giants of the Cretaceous disappeared, these survivors began to define the shape of the future. Small, feathered, and capable of flight, they inherited a world stripped of massive herbivores and apex predators, a landscape where ecological niches remained open and competition was reduced. Over millions of years, these lineages radiated into new forms, occupying niches across the globe. Modern birds, from the tiniest hummingbird to the largest raptor, bear testament to this legacy, a living continuity of survival, adaptability, and evolutionary innovation. The landscapes they inhabited were slowly recovering. Vegetation returned in pockets, rivers resumed their flow, and insects and small invertebrates recolonized decimated ecosystems. In this recovering world, early birds exploited resources unavailable to larger creatures, moving through dense understories or along forest edges, foraging in small groups or alone. Fossil evidence of feeding marks, tracks, and nests captures these interactions, providing insight into the delicate balance that allowed survival and eventual proliferation. Ultimately, the story of the birds is a story of resilience and continuity. They remind us that extinction, while dramatic, is selective rather than absolute. Traits like small size, mobility, dietary flexibility, and behavioral adaptability can become decisive advantages in the face of extreme environmental upheaval. Fossils preserve the anatomical and ecological threads linking pre- and post-extinction life, revealing a lineage that survived not by strength, but by finesse and the ability to navigate a world transformed. As one imagines the immediate aftermath of the impact, it is striking to visualize these survivors. Small, feathered creatures navigating charred forests, foraging along rivers, and seeking refuge from extreme conditions. They embody life's capacity to endure, adapt, and persist, even when ecosystems collapse around them. Fossil evidence preserves this narrative with astonishing clarity, connecting deep time with the present and reminding us that the echoes of ancient lineages continue to shape life on Earth. In tracing the survival of birds, we see not just the preservation of a lineage, but the emergence of a foundation for the ecosystems that would follow. Their endurance ensured that life continued to evolve, radiate, and occupy niches once dominated by now extinct giants. Fossils, feathers, and skeletal remains offer a window into this profound transition, highlighting the traits and behaviors that allowed these species to persist and thrive where others could not. Through this lens, the modern sky is a living reflection of ancient resilience, a bridge across a world transformed by extinction and recovery. Though the age of dinosaurs came to a definitive close, their presence endures in stone, sediment, and amber. Fossils serve as time capsules, preserving the intricate details of creatures long vanished, from the massive sauropods that once roamed vast plains to the tiniest feathered birds that survived cataclysm. Every bone, every imprint, every fragment tells a story of anatomy, behavior, and ecology, allowing us to reconstruct worlds that no longer exist, yet continue to speak through the layers of Earth. In fossil beds across continents, the skeletal remains of giants lie embedded in sediment, each layer recording a moment in deep time. Their sheer size is preserved in humerus and femur, vertebrae stacked like the ruins of ancient towers, articulating a structure designed for strength, mobility, and endurance. Yet alongside these colossal forms lie the delicate traces of smaller species, bird-like dinosaurs, early mammals, and insects preserved in amber, capturing fleeting moments in exquisite detail. This juxtaposition illustrates the spectrum of life that persisted, vanished, or adapted, offering a complete, if fragmented, vision of ancient ecosystems. Trace fossils reveal more than mere presence. They reveal behavior. Footprints etched into ancient mudflats record the gait of a sauropod, the careful hunting steps of a theropod, or the cautious movement of a small ornithischian. Burrows, nests, and feeding marks preserve evidence of social interaction, reproductive strategy, and dietary choice. In these subtle impressions, we witness the rhythms of daily life, the tension between predator and prey, and the evolving strategies of survival. Each mark is a whisper of a past world, a tangible connection to creatures that walked, fed, nested, and endured long before humans observed their traces. Amber preserves even more intimate details. Feathers, hair, and the minute exoskeletons of insects. These specimens offer a window into anatomy and ecology, capturing moments of life frozen in resin. Microscopic structures, coloration patterns, and preserved soft tissues reveal the intricate adaptations that allowed survival, from thermoregulation to camouflage. These tiny remnants illuminate the continuity of life, bridging the gap between extinct lineages and their modern descendants, while providing unparalleled insight into the richness and complexity of prehistoric ecosystems. Sedimentary layers act as chronicles of environmental change. Shifts in rock composition, mineral content, and fossil density trace the ebb and flow of ancient climates, the arrival of catastrophic events, and the subtle rhythms of recovery. Each stratum offers context, linking biological remains to the physical world they inhabited. By examining these layers, paleontologists reconstruct not only species, but ecosystems. Forests, floodplains, deserts, and coastal zones come alive through the careful interpretation of sediment and fossil. These records reveal the resilience, adaptability, and vulnerability of life, offering a profound narrative of evolution and extinction. The preservation of fossils also allows a study of evolutionary experimentation. From the early Archosaurs to the rise of feathered dinosaurs and birds, these remains illustrate incremental changes in anatomy and behavior. Hollow bones, specialized limbs, dentition patterns, and feather structures all record adaptations that shaped survival strategies and ecological roles. Fossils bridge epochs, showing both continuity and innovation, providing evidence for how species responded to environmental pressures, competed for resources, and exploited new opportunities. As we drift across these ancient landscapes through the lens of fossils, the interplay between life and death becomes clear. Each skeletal remain, fossilized leaf, and amber-entombed insect tells a story of existence, persistence, and vulnerability. Mass extinctions, environmental shifts, and evolutionary breakthroughs are etched into stone, revealing the dynamic history of a planet in constant transformation. Fossils do not merely record anatomy, they preserve the memory of interactions, ecosystems, and the subtle balances that sustained life. Exploring fossil sites, one becomes aware of the patience of geological processes. Burial, mineralization, and preservation occur over millions of years, slowly transforming organic remains into enduring records. The act of discovery, unearthing these treasures from sediment, is a journey into the deep past. Each fossil, whether fragmentary or nearly complete, becomes a key to understanding worlds long vanished, offering insight into the behaviors, environments, and adaptations of creatures that shaped the Mesozoic era. In examining these remnants, we recognize the legacy of the dinosaurs, not just in their physical forms, but in their influence on modern ecosystems. Birds, the living descendants of theropod dinosaurs, soar through the skies as living echoes of extinct lineages. Mammals, insects, and plants continue to occupy niches once dominated by their prehistoric counterparts. Fossils remind us that life persists, adapts, and evolves, even in the face of catastrophic change, and that the story of Earth is a continuous, interconnected narrative written across millions of years. The tactile nature of fossils, bones, teeth, claws, and feather impressions, allows us to reconstruct movement, posture, and behavior. Paleontologists infer hunting strategies from dentition, feeding habits from stomach contents, and social behaviors from trackways and nesting sites. These silent records convey the rhythm of ancient life, the stalking of prey, the migration of herds, the nesting of birds, and the delicate balance of predator and prey. In essence, fossils are the memory of life itself, an enduring archive that transcends time, offering a bridge between the vanished past and the living present. As the study of fossils continues, each new discovery deepens our understanding of the vast tapestry of life. Even fragmentary specimens can illuminate evolutionary relationships, ecological interactions, and the consequences of environmental upheaval. The continuity of research allows us to trace lineages from the dawn of reptiles through the rise of dinosaurs, the cataclysms of mass extinction, and the survival of small adaptable species into the modern age. In this way, fossils become more than records. They are storytellers, connecting us to a world both alien and familiar. Ultimately, the fossil record embodies the delicate balance between fragility and resilience. It captures the rise and fall of species, the emergence of new forms, and the enduring legacy of lineages that adapted to a changing world. It is a testament to life's persistence across deep time, a reminder that even in the face of extinction, the threads of continuity can endure, leaving traces that inform, inspire, and captivate. In every fossilized bone, feather, or footprint lies the echo of a vanished world, preserved in the earth itself, inviting reflection on the continuity of life and the enduring narrative of evolution. As our journey through the rise and fall of dinosaurs comes to a close, allow yourself to sink even deeper into relaxation, surrounded by the ancient calm of a prehistoric world. Feel the gentle sway of ferns, the soft rustle of distant leaves, and the quiet presence of creatures that walked the earth long before us. Sense the lingering echoes of continents drifting slowly apart, the warmth of ancient sunlight fading across the plains, and the subtle memory held in stone, bone, and fossilized footprints. Let your thoughts slowly fade, your muscles soften, and your breath flow naturally and effortlessly as the story of life, extinction, and what remained wraps around you like a gentle, timeless embrace. If you enjoyed this peaceful exploration, please consider leaving a like, subscribing, or sharing your thoughts below. Your support helps others discover this tranquil journey to the past. You can also turn on notifications so you don't miss any of our future adventures together. For now, rest here fully supported. Let your body relax, release any tension, and allow your mind to wander freely through the ancient lands of your dreams. Good night and sleep well.